Hello students, I welcome all of you in this lecture. In this lecture we are going to discuss map induced on spectrum of a ring. Okay, but before that I will discuss some basic terminologies that we need in this lecture. So in the last lecture we talked about V of I, that means we talked about this particular concept that V of I, that is set of all prime ideals which contain I. Okay, now first of all I'm going to define one new concept here. So let me define that concept. Let A be a ring and small a belongs to capital A, be an element. Okay, then we define XA, where X is spectrum of A, right? How we define it? As we define XA as XA equal to set of all prime ideals in spectrum of A which do not contain A, which do not contain element A. Okay, what does this mean? This means we will find V of A. Okay, first of all we will find the set of all ideals which contain A. Okay, and then we'll take the complement of this V of A in spectrum of A. Okay, so I can write it in a simpler words that it is nothing but a complement of V of A, that means set of all prime ideals which contain A, okay, in spectrum of A. That is your XA. Okay, so again we can define it as set notation like this, that prime ideals P belongs to spectrum of A such that A does not belongs to P. Okay, A does not belongs to P. Anyway, now after definition of this particular concept we will define extension and contraction of ideal. So let me go for that. Let F from A to B be a ring homomorphism. Okay, and I be an ideal of A. Then we know that f of I need not be an ideal of B, because f of I is an ideal of B if f is surjective. Okay, if f is surjective then its image is ideal. Unless and until f is not surjective we can't predict that f of I is an ideal. So what we do, basically, suppose this is your ring A, right, and suppose this is your ring B. You have already defined a map F between these two rings. Okay, now I is an ideal of A. Okay, then this is your I. Suppose image of I is this is your f of I. Now this f of I is need not be an ideal. Okay, so what we do, we generate an ideal by the set. Okay, so first of all we have I, then we'll find out its image, that is f of I, and then we generate an ideal by this particular set. Okay, let me just say, suppose that ideal generated is this. Okay, this is an ideal which is generated by this particular f of I. Okay, ideal generated by f of I. Okay, so this is a complete ideal generated by f of I. So this ideal is called as extension of ideal I. Okay, so we generally call it or denote it by I raised to E, that is extension of ideal E. Okay, so in short I can write I raised to E, that is extension of ideal, is equal to ideal of B generated by f of I. Okay, this is your extension of ideal. Then let's define contraction of ideal. So my next definition is contraction of ideal. So again we are going to take one homomorphism. So let F from A to B be a ring homomorphism. A to B be a ring homomorphism, and J be an ideal of B, then we particularly know that inverse image of ideal is an ideal always, right? Then clearly F inverse of J is an ideal of A, right? And this ideal is called as contraction, okay, contraction of J. So J contraction is equal to F inverse of J, okay. And in addition to that, if J is prime ideal, then F inverse of J is also an prime ideal, which is used for the inducing the map F from A to B on spectrums, okay. So these are three important concepts that we are going to use in the upcoming theorem. So let me write the theorem now. Theorem: let phi from A to B be a ring homomorphism. Let phi from A to B be a ring homomorphism, okay. Let capital X is equal to spectrum of A, that is set of all prime ideals of A, and capital Y be the spectrum of B, okay. If ideal Q belongs to Y, definitely if ideal Q belongs to Y, that is it's an ideal of B, then its inverse image is an ideal of A, as we define contraction, right? If Q belongs to Y, then phi inverse of Q is a prime ideal of A, is a prime ideal of A, right? That is phi inverse of Y belongs to X. Let me just correct this particular thing. Phi inverse of Q belongs to X, okay. So what happens actually, if you select an ideal from Y, then you can find its pre-image as an ideal of A, that is ideal in X, okay. So definitely we can define a map from X to Y, sorry, Y to X, okay. So what can we say? So phi induces a mapping, phi induces a mapping phi star from Y to X. And how do we define this map? Defined as, if we select an ideal Q of Y, then phi star of Q is nothing but actually phi inverse of Q, okay. So phi inverse of Q is ideal of A, okay. Then this particular induced map satisfies some of the properties, so let us see them one by one. So very first property, first thing, if A belongs to A, if A belongs to A, okay, then phi star inverse, phi star inverse of XA is equal to Y phi of A, okay, Y phi of A, and phi star is continuous. Phi star is continuous, okay, no problem. Now already we know what is XA, okay, so let's go to the proof. We already know what is XA. We have XA is equal to all ideals P belongs to spectrum of A such that A does not belongs to P, okay. So it is in V of a complement, right? It's V of a complement. Let's not use this notation, we will just go with the simple definition. Fine. Now let's do one thing, let's try to prove our cause. Yeah, so first of all, what I will do, I will take one ideal from phi star inverse of XA. Let Q be ideal that belongs to phi star inverse of XA. So that clearly implies that phi star Q belongs to XA. So phi star Q belongs to XA, okay. phi star q, by definition it is nothing but phi inverse of q, so that means phi inverse of q belongs to xa. Okay, now if you phi inverse of q belongs to xa, then by definition of xa, a does not belongs to phi inverse of q. Okay, now if a does not belongs to phi inverse of q, it's quite clear that image of a does not belongs to q, so phi of a does not belongs to q. Okay, and if phi of a does not belongs to q, what does this mean? This means q is ideal which does not contain phi of a. So where does q goes? So q belongs to y. It's an ideal of y. Okay, it's an ideal of, it's an element of y, okay, which do not contain phi of a. So it belong, that particular idea belongs to y phi of a. Okay, y phi of a is what? Set of all ideals from spectrum of b which do not contain phi of a, right? So q belongs to y phi of a. Okay, fine. Conversely, let me now go to the converse part. So that is what happens here now. So phi star inverse of xa is subset of y phi of a. Now conversely, let me take one element from y phi of a. Conversely, let q dash belongs to y phi of a, right? So what does this implies? This implies phi of a does not belongs to q dash, because q dash belongs to y phi of a. So by definition of that particular set, phi of a cannot be in the q dash. So if phi of a is not in the q dash, that simply means a does not belongs to phi inverse of q dash, right? Now if a does not belongs to phi inverse of q dash, then what does this mean? This simply means a does not belongs to phi star of q dash. Okay, so what does that mean? That means phi star of q dash. So q dash belongs to phi star inverse of xa. But how can I be sure about it? So let me tell you. So that means a does not belongs to phi star of q dash. That means phi star of q dash does not contains a. So this particular set belongs to xa. Okay, and since this belongs to xa, okay, q dash belongs to phi star inverse of xa. Right, simple. Q dash belongs to y phi of a, so phi of a does not belongs to q dash, so it does not belongs to phi inverse of q dash. So by definition, it does not belongs to phi star of q dash. Okay, it does not belongs to phi star of q dash. That means phi star of q belongs to x of xa, because it does not contains a. So q dash belongs to phi star inverse of xa. So what does this mean? So y phi of a is subset of phi star inverse of xa. Y phi of a is subset of phi star inverse of xa. So definitely we can combine these two statements, and thus we can write that phi star inverse of xa is equal to y phi of a. Okay, now let's go to the second part of this. If I is an ideal of a, okay, then phi star inverse of v of I is equal to v of I extension. Okay, so we already defined I extension, so let's directly go to the proof now. Okay, fine. So let me first of all select one element from phi star inverse of vi. Okay, so let q belongs to phi star inverse of v of I. So this simply means, this implies phi star of q belongs to v of I, right? Phi star of q belongs to v of I. Now since phi star of q belongs to v of I, this implies I is contained in phi star of q. I is subset of phi star of q, because v of I means set of all prime ideals which contains I, right? So phi star of q belongs to v of I, that means I belongs to phi star of q. Okay, I is contained in phi star of q. So what this means, this implies I is contained in phi inverse of q by definition of phi star, right? So this implies phi of I, let me apply phi on both sides, phi of I is contained in phi of phi inverse of q. So that means phi of I is contained in q. Now phi of I is contained in q. So what does that mean? Phi of I is contained in q. That means it is nothing but actually I extension, right? So I extension is contained in q. Okay. So phi of I is contained in q. So ideal generated by phi of I is contained in q. So I extension is contained in q. Because basically what happens, phi of I is an is may not be an ideal, right? So we find extension. So basically what happens, suppose this is phi of I, okay, and this is contained in q. Q is ideal, but I extension is the smallest ideal which contains phi of I, right? So definitely I extension must be contained in q. That's the reason behind this. Okay, so I raised to e is contained in q, and since I raised to e is contained in q, we can easily write that q belongs to v of I raised to e. Okay, because I raised to e is contained in q, so q belongs to v of I raised to e. So we can write, so phi star inverse of v of I, okay, is contained in v of I extension. Now conversely, let's assume some element from v of I extension. Conversely, let q dash belongs to v of I extension, right? So by definition of v of I extension, this implies I extension is contained in q dash, right? Okay, so if I apply phi inverse on both sides, then phi inverse of I raised to e is contained in phi inverse of q dash. Okay, but phi inverse of I raised to e is nothing but I, because I extension is a, this is your I, right? Then you find out phi of I. Okay, let's say I extension. Okay, so suppose this is your phi of I, this is your I extension. Okay, so phi inverse of I extension definitely contains, definitely containing phi inverse of q dash. So actually what happens if we take the pre-image of this, because this ideally generated by phi of I. Okay, so pre-image must contain I, right? Pre-image must be equal to I. So clearly by definition, phi inverse of I extension must be equal to I. So I is contained in phi inverse of q dash. So that implies phi of I is subset of q dash, right? And phi of I is subset of q dash. So what does that mean? So q dash belongs to, or we may say that here, just a second here. So I is contained in phi inverse of q dash. So we can say that phi inverse of q dash contains in v of phi. Phi inverse of q dash is a belongs to v of I, because it contains I, right? This particular ideal contains I, so this particular ideal belongs to v of I, right? Okay, now what does this mean? This means q dash belongs to phi of v of I, right? Or we may do one thing, as per our target we can just ignore this step here, and we can directly use the map phi star. So phi inverse of q dash is nothing but phi star of q dash. So phi star of q dash belongs to v of I, right? So where does q dash goes? So q dash belongs to phi star inverse of v of I. So that proves the reverse inclusion, that is v of I extension is subset of phi star inverse of vi, right? So if you combine these two statements together, we can write down our final target. Hence phi star inverse of v of I is equal to v of I extension. Okay, now let's go to the third part of this theorem. Okay, so if J is an ideal of P, if J is an ideal of P, then closure of phi star of Vj, phi star of V of J closure, okay, is equal to V of J contraction. So proof is quite simple. Okay, so let's go to the proof. Okay, so what I will do, first of all, let us take P belongs to phi star of, so let us take P belongs to phi star of Vj. So let P belongs to phi star of V of J, right? So what this implies by definition, if P belongs to phi star of V of J, that means P belongs to phi inverse of V of J, right? So what does that mean? That means phi of P belongs to V of J. Phi of P belongs to V of J, that means J is contained in phi of P. Okay, so J is contained in phi of P. Okay, so if we take inverse image on both sides, then phi inverse of J is contained in phi inverse of phi of P. So what this means, that means phi inverse of J is subset of P. Phi inverse of J is subset of P. So what is phi inverse of J? Phi inverse of J is nothing but J contraction that is contained in P. Okay, so J contraction is contained in P, that means P belongs to V of J contraction. Okay, so P belongs to V of J contraction. Now since P belongs to V of J contraction, see, P contains J contraction, so definitely P is primary which contains J contraction, so P belongs to V of J contraction. Okay, so what does this mean? I took P from phi star of V of J, right, and I've showed that it belongs to V of J contraction. So phi star of V of J is subset of V of J contraction. But in Zariski topology, we have seen that these kinds of sets, V of A, V of I, are nothing but closed sets in this Zariski topology. So this set is closed. Okay, so if this set is contained in this closed set, then its closure must be contained in this set, because this set is itself closed, right? So its closure cannot go beyond this set. So definitely what can I write? This implies phi star of Vj closure. Phi star of Vj closure is subset of V of J complement, because V of J contraction, because V of J contraction is closed. Okay, now let's go to the reverse part of this. So for that, let P dash belongs to V of J contraction. So conversely, let P dash belongs to V of J contraction. Okay, so by definition of V of J contraction, if P dash belongs to that particular set, that means P dash contains J contraction. So J contraction is subset of P, right? Now if J contraction is subset of P, by definition of contraction, J contraction means phi inverse of J is subset of P. So if phi inverse of J is subset of P, that means J is subset of phi of P, right? Now J is contained in phi of P, right? Okay, no problem. So phi of P, let me just phi of P dash, J, phi of P dash contains J. So phi of P dash is an ideal which contains J. So this ideal belongs to V of J. Is it? Okay, so phi of P dash belongs to V of J. So where does P dash goes? So P dash belongs to phi inverse of V of J. But phi inverse of V of J is contained in phi inverse of V of J closure. So P dash belongs to phi inverse of V of J closure. Okay, because every set is contained in its closure. Okay, so this implies P dash belongs to phi star of phi inverse of V of J means phi star of V of J closure. So this proves reverse inclusion, right? So V of J closure. So what I showed, that is V of J contraction is subset of phi star of V of J closure. Thus, if we combine these statements together, we can write our final target, that phi star of V of J closure is equal to V of J contraction. Okay, now we will move to the next part of this theorem. Let me move to that part. If phi is surjective, if phi is surjective, then phi star is a homeomorphism, is a homeomorphism of Y onto the closed subset of V of kernel of phi of X. Okay, so let's go to the proof now. Yeah, so first of all, suppose that phi is surjective. Suppose phi from A to B is a surjective ring homomorphism. Assume that it is surjective ring homomorphism, right? Then by first isomorphism theorem, domain upon kernel is isomorphic to image, but we say that phi is surjective, so image is B. So A upon kernel of phi is isomorphic to B. Okay, A upon kernel of phi is isomorphic to B. Now what happens by one-to-one correspondence? If we will see this one-to-one correspondence, because these two sets are isomorphic to each other, right? Okay. So clearly by one-to-one correspondence theorem, what we can write here is this. See, now let me show you. These two sets are isomorphic, so by one-to-one correspondence, suppose here I am considering the ideals of A upon kernel of phi. So definitely the ideals of A which contains kernel of phi. So ideals of A which contain kernel of phi, and here I am considering ideals of B. So definitely there is one-to-one correspondence. For every ideal of A which contains kernel of phi, there is ideal of B, and for every ideal of B there is some ideal of A upon kernel of phi. Okay, so there will be some ideal of A which contains kernel of phi, right? So what does this mean? So suppose J is ideal of B. Okay, J is ideal of B. So definitely there is some ideal of I of A which contains kernel of phi. So this contains I contains kernel of phi. That means kernel of phi belongs to, or that is just V of kernel of phi, right? Because V of kernel of phi, because I contains kernel of phi, right? So kernel of phi, just see the definition. We know this V of I. What is V of I? Ideals such that ideal contains I is contained in P. So here kernel of phi is contained in I, so kernel of phi is contained in I, so that clearly means that I belongs to V of kernel of phi. That's it. So what does happens here? Just look at this. So J, so this is completely, what can I say, phi inverse of J. So this is inverse image of J, right? So phi inverse of J is equal to ideal of A upon kernel of phi. Okay, so phi inverse of J is equal to ideal of A upon kernel of phi. So phi star of J is equal to ideal of A upon kernel of phi. So definitely phi star of Y. So let me just erase all these things and let me have a simple and clear discussion of this with you. So let me show you now. So suppose J, let me write here, by one-to-one correspondence, Okay, every ideal, or we may say in short that there is one-to-one correspondence between, let me write it in a precise way. So there is one-to-one correspondence between ideals of A which contain kernel of phi and ideals of B. So if I consider if that is if J is ideal of B, then inverse image of J. Okay, so what can we say? Then inverse image of J is equal to some ideal of A which contains kernel of phi. So what can I say in short? In short, I can say that V of kernel of phi means set of all ideals of A which contains kernel of phi is exactly equal to phi star of Y, which is Y is the spectrum of B, that is set of all prime ideals of B. Okay, phi inverse of Y. So definitely this is the correspondence, right? And what happens? And phi star induces, this is quite clear now, phi star induces bijective and continuous map, from Y to V of kernel of phi. Okay, fine. Now only thing remains to prove is this phi star inverse is continuous. That is what we want to, because already we have found out there is a map from Y onto the V of kernel of phi. So I just want to prove that that map is homeomorphism. And if I want to that map is homeomorphism, I need to prove that its inverse is continuous. Okay, so my claim is phi star inverse is continuous. Phi star inverse is continuous. So for that, let me take one element, closed subset. So let Y dash be a closed subset of be a closed subset of Y, right? So this implies by definition of Zariski topology Y dash is equal to V of J, okay, for some ideal J of, for some ideal J of B, okay. So what this implies, definitely I will be equal to phi inverse of J, right? So V of J and I equals to phi inverse of J, so I contains kernel of phi, right? Okay, now see what happens. P belongs to phi star of Y dash, that means phi star of Vj, if and only phi of P belongs to Vj. So what can I write here? P belongs to phi star of Y dash. When this is possible, that P dash belongs to phi star of Y dash, that is phi star of Y dash means phi star of Y dash means V of J. So when P belongs to phi star of V of J, this is possible if and only if P belongs to phi inverse of V of J by definition, and that is possible if and only if phi of P belongs to V of J. Okay, now that is possible if and only if, just a second, phi of P belongs to V of J if and only if J is contained in phi of P, right? And that is possible if and only if phi inverse of J is contained in P, right? So that is possible, phi inverse of J is contained in P, that is possible if and only if P belongs to V of phi inverse of J, right? So that is if and only if P belongs to V of J complement, right? So what does this means? So this means phi star of Y dash means phi inverse of Y dash, inverse image of closed set, because Y dash was closed, right? So we took P belongs to phi inverse of y dash, so that implies phi star of y dash is equal to V of j contraction. That means phi inverse of y dash is equal to V of j contraction, which is a closed subset. So that means that is inverse image of closed set is closed. Inverse image of closed set is closed. So phi star is a homeomorphism. So phi star is a homeomorphism. Okay, that's the proof. Now let's move to the fifth statement of this theorem. If phi is injective, if phi is injective, then phi star of y is dense in X. So if phi is injective, then phi star of y is dense in X. Okay. Now let's prove this. Proof. What is phi star of y closure? Okay. Because we have to show that phi star of y is dense in X, this means phi star of y closure should be equal to X. That is the only condition that we need to prove, right? So phi star of y closure, what is that equal to? So that is equal to phi star of y means V of 0. We have seen this closure. So that is equal to V of 0 contraction. We have seen this in the previous part. But 0 contraction is kernel. So that is equal to V of kernel of phi. Right? Okay. So now I want to find out when phi star of y is dense in X. Okay. So let's find it. So phi star of y closure is equal to V of kernel of phi. Right? That means okay. So we will establish a condition when phi star of y is dense in X, and then we'll prove that if phi is injective, then definitely phi star of y is dense in X. So first of all, phi star of y closure is equal to phi star of V of 0 closure, but V of 0 closure, that's why previous part we have done it. So V of 0 contraction, so that is V of kernel of phi, because 0 contraction means phi inverse of 0, and pre-image of 0 is nothing but kernel of phi, so that is V of kernel of phi. Now let's try to understand what is condition required for this particular phi star of y to be dense. So let's have a look here. So phi star of y is dense in X if and only if its closure equal to X. So if and only if phi star of y closure is equal to X. Okay, when that is possible? That is possible if and only if we have found the value. So V of kernel of phi is equal to X. That is possible if and only if kernel of phi is contained in P for every prime ideal in X, because V of kernel of phi is X. That means spectrum of A, right? So every prime ideal of A contains kernel of phi for every prime ideal of A, right? That is possible if and only if kernel of phi is contained in intersection of every prime ideal. So intersection of P, where P is a prime ideal, or P belongs to, we say, spectrum of A. So intersection of all prime ideals, but we know that intersection of all prime ideals is nil radical. So if and only if kernel of phi is contained in nil radical, right? Okay, but now what is given to us? We have given that phi is injective. In our case, we have phi is injective, right? So what this implies? This implies kernel of phi is equal to singleton 0, and 0 element is always in radical, right? So singleton 0, clearly, let me write it clearly. Clearly, singleton 0 is contained in nil radical. right? So that's why this condition has been satisfied. So that's why phi star of y is dense in X. So this implies phi star of y is dense in X. And let's go to the final part of this theorem. If psi from B to C is another ring homomorphism, one is given in the statement of theorem, is another ring homomorphism, okay, then psi composite phi star is equal to phi star composite psi star. Okay, so this is very simple to prove. Okay, now what is psi composite phi? It's quite clear. Psi composite phi is a map from phi goes from A to B and psi goes from B to C. So this is map from A to C. Okay, so this implies it induces a map psi composite phi star, and that is map from spectrum of C to spectrum of A, right? Okay, so let's find out what is exactly this. So let us consider, let Z equal to spectrum of C, because we already have a spectrum of A as X. Okay, fine. Let R belongs to Z. So R is a spectrum of C, so it is prime ideal of C. Okay, now what is psi composite phi star of psi composite, then psi composite phi star of R? So by definition this is equal to psi composite phi inverse of R, right? But psi composite phi inverse means phi inverse composite psi inverse of R, right? So this is phi inverse of psi inverse of R, okay, but this is equal to phi inverse of, okay, psi inverse of R, but phi inverse of something means phi star of something, right? So what can I write here? So this is equal to phi star of psi inverse of R. So this is equal to phi star of psi star of R. So phi star composite psi star of R, and this happens for every R. Okay, so what this implies, psi composite phi star, this map is equal to phi star composite psi star. That's it. Okay, so that was the last part of this. So let's have a recap of whatever we have seen in this lecture. So first of all, we introduced three basic concepts: what is XA, what is extension of ideal, and what is contraction of ideal. Okay, and then we proved that if phi is ring homomorphism, then it induces a map homomorphism on spectrums. Okay, and that particular map satisfies these many conditions, that phi star inverse of XA is equal to y phi. Okay, then we proved that if phi is an ideal of A, then phi star inverse of V of I is equal to V of I extension. Then if J is an ideal of B, then phi star of Vj closure is equal to V of J contraction. Then we showed that if phi is surjective, then phi star is a homeomorphism of Y onto the closed subset of V of kernel of phi. Okay, by showing that inverse image of closed set is closed set. Then we proved that if phi is injective, then phi star of Y is dense in X. And then we proved that if psi from B to C is another homomorphism, then psi composite phi star is equal to phi star composite psi star. Okay, so with this I stop here in this lecture. Thank you.